This lecture is all about force vectors. We're going to learn about vector operations and how we add forces, because they're just vectors, and how we work with vectors, and why you would want to. After we're done today, you should be able to resolve a two-dimensional vector into its components and add two-dimensional vectors using Cartesian vector notation. Now, there are several things in these slides that are on the course website that we will not cover. However, that's just because you're watching it online instead of in person, of course. You should go through all of the example problems and group problem-solving problems as examples as well in your study of the topics of the course. The examples I've recorded for you are probably a little more critical because there's more thought process behind them, but there's at least a few more items in the slides on the course site for you to review. So why would we care? Why would we care about adding vectors together? Well, the course the central topic of the course is force. Force is something that has direction. If you want to lift a box, for example, you can't lift a box by pushing downward on it. You must push up. The direction that you apply the force makes a difference. And if you think of people playing tug of war, people on each side of a chasm, imagine with a rope. Well, each team is pulling in the opposite direction. As long as they have equal force, neither one will pull the other over the chasm or over the line, as long as the force is balanced. If those forces don't, then obviously one team is going to start moving. But you can't have a team on one side pulling to the right and a team on the other side also pulling to the right. That doesn't work. So the direction that the force is applied makes a difference. And we can't just say, well, how much force is there? You might have gotten used to this by thinking of your weight as a force, which it is. But if you think about it, you'll realize that your weight acts downward. It has a direction associated with it. If your weight acted upward, you would simply fly off the surface of the planet. That wouldn't be good. So thank God that force has a direction, right? Your weight is an example of force. So anyway, how do we add forces? Well, let me give you a brain teaser. What's 3 plus 4? You might say, well, that's not a brain teaser. Not at all. 3 plus 4, that's simple. That's 7. Is it really? I claim that 3 plus 4 can be equal to 5. Not always, but it can be. How? How can 3 plus 4 be equal to 5? Well, think about it. If you walk 3 paces up and 4 paces to the right, what's the total distance you've traveled? Well, you've traveled along the base and the height of a right triangle, and it's a 3, 4, 5 triangle. So 3 plus 4 is 5. If you include direction, you see. Most of the time when we add numbers, we're adding numbers along a single line, the number line. That number line just is a straight line that does not change direction. But as soon as you change the direction, or you have a need for changing direction, then numbers by themselves are inadequate. So a vector is something that has both magnitude and direction. Now, when I first learned about vectors, it confused me to no end. I didn't understand that all we were really doing is mashing together a magnitude with a direction. They never became just one entity. We just put them together because they belong together, because the direction information along with the magnitude, the length information, was useful. We could use it to do things. And that's why we have numbers in the first place. Why do we bother with, numbers? For example, 1, 2, 3, 4, 5. Well, because we can use those numbers to represent a count of things. And that's a very useful concept to have in our day-to-day life. For a long time, you may or may not know, the number 0 was not accepted, or negative numbers were not accepted. Why do you need negative numbers? How can you have negative 5 apples? That makes no sense. So why do we need this thing? In the same way, why do we need vectors? Why do we need something where we've mashed together a number with a direction? Well, if I tell you that, you need to go from here to your home, and let's say your home is 5 miles away, and I tell you, well, go. Okay, what direction, right? If you don't go the right direction, you don't get home. So direction is very important, as well as magnitude. Anyway, so in our particular example here, we've got three forces. They're called concurrent forces because they're all applied at the same point. But anyway, these forces are acting on they basically add together to act on a hook. Now you'll notice there's a shackle that connects the chains together ultimately, and the hook is applied to the shackle. But if the question is not so much the shackle, but how much force must that hook resist, well, you'll notice that force 1 and force 2, as well as force 3, which are all in white, they would add together, and notice that some sideways component of these forces would cancel out. It's like a game of tug of war where one's pulling one way and the other side's pulling the other, and a portion of that force is unnecessary to consider because it cancels out. In fact, the vector in red is the resultant force. It's the sum of all of those forces, taking into account the direction. Just like a moment ago, I claimed that 3 plus 4 is 5, because if you take into account a direction, go north 3 paces and east 4 paces, and you have gone 5 paces from your starting point, okay? Anyway, so there are three concurrent forces, and if we need to know how big a hook we need, we probably should be able to figure, or we probably have to find a way to calculate the sum of all those forces. So we'll need direction information on each of the forces, as well as their magnitude, in order to add them together. Because if let's say you only had two forces and they're pulling opposite each other, well, then the hook doesn't need to support any force, right? The shackle that holds the two chains together, sure, it has to support force, but not the hook attached perpendicular, essentially, to the chains. Let's consider scalars and vectors and kind of contrast the two, because you're very used to scalars, but vectors are probably something that's a little bit new to you. So you've been dealing with scalars for a long time, things like mass and volume. These are things that have no need for a direction, but force and velocity really need direction. If I ask you, for example, two cars are both going at 100 miles an hour and they collide with one another, they touch, what happens? You might say, well, obviously, both occupants of the vehicle tragically die, because you've got 200 miles an hour, net difference in speed, and no cars and no bodies are going to stand up to that. Well, maybe, but what if those two cars are not going in opposite direction playing chicken? What if they're drag racing? What if they're going side by side and they just barely have a difference in velocity, where they just slightly veer into one another? Well, the relative velocity between them is very small because of the direction, you see. If the direction is opposite, then the relative velocity, the difference in velocity between the two, is very, very high. There's going to be a wreck and there's going to be a problem. But if the direction of the velocities is essentially the same, there's not much relative velocity between the two, and probably there might be a scrape or something. Hopefully the wheels don't run into each other, but I guess I should say at this point you shouldn't be drag racing anyway. But you get the idea that there's a need for direction that scalars don't fill by themselves. The characteristics of a scalar versus vector, well, a scalar has magnitude, positive or negative, basically along one single line, the number line. That's it. Whereas vectors is really just a marriage of magnitude and direction. That's all it really is. It's nothing more or less. And why do we need them? Well, because they're useful. That's why we need them. That's just like numbers. Why do we need numbers? Because they're useful. Now, there's simple arithmetic that is associated with scalars, simple operations that you are used to: multiplication, division, addition, subtraction. You're used to all those. But for vectors, we've got to determine some new operations. We have to figure out how to work with vectors, because once you've got direction associated with a number, things are a little bit different. Just like I gave you the simple example before of 3 plus 4 is what? Well, 7 is your normal answer. But if direction comes into the picture and is part of the game, then 3 plus 4 can be 5, right? Because those two lines are perpendicular to one another. So anyway, we need to learn something called the parallelogram law, which I will describe to you, and how we notate vectors. Most of the time what we'll do is use a bold font, or put a line above the vector symbol, or we'll use an arrow or a caret. I'll show you in the context of examples how we indicate vectors. And you'll see in the slides how vectors are indicated. So these PowerPoint presentations, you'll see a vector represented in italics, bold, red, etc. You'll begin to recognize them. They're pretty easy as we go. So what operations can there be with vectors? Well, as the scalar part of the vector, because the vector still has a scalar part as well as the direction, we can use scalar multiplication and division. So you notice on the left-hand side, we've got an arrow, a vector. It has a direction. You can see the direction it's moving. And it has a certain length. The length of the vector represents the magnitude of the vector. That's the scalar part, okay? The length of the vector is the scalar part. We can simply multiply the length by 2, and we'll get a resultant vector that's twice as long as the first one. Its scalar piece has increased by 2. Its direction hasn't changed, but its scalar piece has. We could multiply the original vector by -1. In that case, the direction has not changed. Be careful. You can say, yeah, but it's pointing the other way. Yes, but it still lies along the same line. Okay, it's simply a negative magnitude of what it was before. Okay, so we wouldn't necessarily always say that the direction of the vector has changed, even though the head's on the other end and it's pointed the other direction. Of course, we can multiply by -1/2 and get a vector that is smaller than the original vector and points in the opposite sense, although along the same line as the original vector. So scalar multiplication and division work just fine with vectors. You can use those all day long. How do you add vectors? Well, with vectors, we have to take into account their direction. So think about it as I described earlier. 3 paces north, 4 paces east, and you've generally gone northeast, right? 5 paces. So all we really do there is take the vectors and set them head to tail in order to determine their final position. There's another way to do this, though, using what's called the parallelogram law, where basically what you do is you set the 2 vectors tail to tail, and you draw 2 lines parallel to each vector. So one line parallel to vector A, another line parallel to vector B. Where those lines intersect, that's the sum of the 2 vectors. And then the resultant vector, the so-called, well, the resultant is simply the sum of the 2. The resultant is simply from the original point, the base point of the 2 vectors, up to the point where the 2 lines cross, okay, indicated as point P in this diagram. One interesting thing about vectors that it took me a while to figure out when I was a student years ago is that vectors can be moved around at will. Okay, they can be. I was used to at the time. I think I'd finished algebra or something by the time I learned vectors, and I was a little confused because I thought, well, I'm used to a point in the grid system in the first, second, third, or fourth quadrant. So how can I add vectors when one's over here and one's over there and they're not even touching? Well, you can move vectors around however you like. You can't change the direction of their magnitude, but you can lay them down wherever you like for the most part. Now, the point where a force is applied to a body makes a difference, but we'll talk about that a little bit later. So if you have 2 vectors, you can simply put them tail to tail, and it doesn't matter where you really start them. We're interested in the sum of the 2. There's also the triangle method, which I alluded to earlier, the tip-to-tail method, where you take one vector and you literally move it so that its tail is touching the tip of the previous vector. And then the resultant vector is simply the sum of the 2. So you move, think about it as walking. So you walk along vector A, walk along vector B. The resultant of that, the net effect of your efforts, are the resultant vector R. It turns out forces work the same way. If you've got a car, okay, and you imagine trying to, say your car breaks down, you're trying to push it off the road. A friend stops to help you, and you're pushing you both get to the back of the car, you're pushing generally forward, but there's a little bit of, angular misalignment between the direction of your forces. Well, it's entirely possible that the lateral or sideways component of the force you're applying to the car will simply cancel out. I mean, certainly, even if you don't have a friend, if it's yourself pushing a car and you have a little bit of lateral force, the tires against the ground will resist that sideways force. The tires only roll in one direction. You're not going to slide the car sideways at the rear. If you're that strong, well, that's impressive, but most people are not, and I seriously doubt that you are. But anyway, the resultant of the two vectors, some of the components can cancel, right? Some of the effort, if you will, or the component of the force can cancel out, and the resultant is simply the sum of the two vectors, taking into account the direction of the vectors. How do you subtract a vector? You do that. Well, it's pretty simple. If you're taking one vector and subtracting another, all you're really doing is adding the negative of whichever vector has a subtraction sign in front of it. That's all you're really doing, right? Think about, again, walking from one point to another. So let's think of going north 3 paces, east 4 paces, but what if we want to take the difference between those two? Well, simply travel south 3 paces and then east 3 paces, right? Or whichever, depends on which vector you want to subtract, but just flip the direction or the sense of one of the vectors, whichever vector you wish to subtract, and you'll find the difference between the two vectors, or the subtraction of one from the other. How could you add more than 2 concurrent vectors graphically? Put them all tip to tail. However many vectors you have, simply move them around in the plane, if we're talking about a 2-dimensional thing, where they are tip to tail, and then go from the tail of the very first to the tip of the very last, and there's your resultant vector. It's really that simple. What is resolution of a vector? Well, it's actually the opposite. It's actually breaking up a vector into its components. So if you have a force F being applied to a point, and you'd like to know how much force is along the U and the V axes, you can actually break up force F into components. What you do is simply draw a line parallel to the U axis from the tip of F, and a line parallel to the V axis from the tip of F. And basically, it's the reverse of the parallelogram law. That's all it really is. And basically, where those two lines land on the V and U axis indicate the amount of length that vector F has along that axis. So the effect of force F on that contact point between, on the end of it looks like some kind of cable or something, those hooks or eyes at the end. The effect that vector F has as a single vector on that point is the same that vector F sub V and F sub U would have, the components of the vector along the V and the U axes. If we were to apply forces at the eye, or the eyes, it looks like, that connection point, equal to F sub V and F sub U, which are components of F, we would get the same net effect because FV and FU add up to F. Now here's what's kind of interesting about it. If you think about it, you'll realize that vector FV and FU, if you just add their scalar quantities together, you will get a number larger than F itself, than the original vector, the light blue vector. And that's actually okay, because if you think about it, F sub V and F sub U have components that cancel. There's a sense in which they're pulling against each other, and that pulling against part cancels out. And you can prove that F sub V and F sub U add to the original vector F by simply putting them tip to tail, as in diagram C. And you see that you have successfully resolved the vector into components along two arbitrary axes. So let's imagine that we have a force F that is in a 2-dimensional plane where we have our usual X and Y axes. Those axes we've been learning about since, grade school, right? And we'd like to know how much force F lies along the X direction and how much lies along the Y direction. Well, we would just resolve that force into components. In other words, draw lines from the tip of force vector F parallel to the X and Y axes. Wherever those lines intersect the X and Y axes represents the magnitude of the force vector F along the axis. For example, F sub Y represents the magnitude of the blue force vector F along the Y axis, whereas F sub X represents the quantity of force in blue vector F along the x-axis. So we simply resolved that force along the x and y axes. So the magnitude of the components of the vector are shown here in the diagram. And the directions, of course, are based on the x and y axes, but we usually use unit vectors I and j to designate the x and y axes. We don't want to reuse x and y. There's a lot of history behind this. You might wonder, well, why do we've already got x, y, and y as names for the axes. Why are we using I and j? Well, I and j aren't actually axes. I and j, in fact, are unit vectors. They are vectors that have length 1. They have unity length. Okay, so you can multiply them by a magnitude and thereby represent the components of a vector. You'll see more what I mean in a moment. For example, we've got our original force vector F on the left under diagram A. You see the blue force vector. You've seen how we can figure out how much of that vector lies along the horizontal axis, how much of it lies along the vertical. Obviously, if we add Fx to Fy in their appropriate directions, I and j, we will get back the original vector F. A way of saying this mathematically is that the force vector F on the left-hand side of the equation, the red, bold, italic F, is equal to the force along the x-axis, and notice that direction is indicated by the unit vector I, so Fx, which is a magnitude, is multiplied by a direction that has magnitude 1, that's the I unit vector, plus Fy, the vertical magnitude of force F, times the unit vector j. You see, I and j are vectors that have length 1 along their respective axes. I goes with x and j goes with y. Now, we don't have to choose that particular system, right? If we had a different vector and needed the components of that vector along two other axes at some other angle, x and y, we could do the same thing, right? If you notice, for example, vector f prime in figure B has a component that moves in the negative direction of the positive y-axis. You see how it goes, Fy prime in the negative j direction, or in other words, negative Fy prime times the positive j direction along the y-axis, okay? So there's many different ways to represent vectors, but notice the key here is that we've got a magnitude, that's the black part of the equation, and the direction, which is the red, bold, italic part of the equation. So we've broken up, or we've written a vector in terms of a reference coordinate system for magnitude and direction. Most of the time, we're going to deal with vectors, if it's in two-dimensional space, relative to an xy axis that are perpendicular to each other. Now, we can turn them or set them at any orientation or inclination that we like as needed to make our life easier in solving problems. So if we want to add vectors, how would we do it? We're finally going to approach what we originally asked, which is how do we figure out how much force is acting on that hook that the chains are pulling on? Well, it's pretty easy. All we have to do is get a reference coordinate system and then write each of the vectors in terms of its components. So resolve F1 into components along the x and y axis. Same thing as F2, same thing as F3. And you see that's been done down in the lower figure. And then all we've got to do is add all of the x components together and then add all the y components together. Now, you won't add the x and the y, just like in my example. You know, if you're moving 3 paces and then 4 in 2 different directions, the final sum is different. You can't say, well, I've moved 7 units away from my starting position just because I've moved 3 units in one direction and 4 in another. No, you have to take into account the direction of motion. So in the same way, we would never take all the x components and add them together, all the y components, and then just add the result together. That's not what we would do. We would leave the x components separate from the y components, but we'll only end up with one x component and one y component by adding them together. Now, another thing we can do is find the magnitude of the resultant vector and the angle where that vector would be located. So you'll see an example of this process here. So we take the vectors, F1, F2, F3, break them into components. So you'll notice that for vector 1, it exists in the first quadrant and therefore has positive I and j components. Those are f1x and f1y. F2, on the other hand, being in the second quadrant, has a negative horizontal or a negative I component. So we end up with negative F2xi, but a positive y component, so therefore F2yj. The third vector, F3, exists in the fourth quadrant, has a positive x component, F3x, in the I direction, and a negative j component, negative F3yj. And then all we do is collect together all of the x components, so f1x minus f2x plus f3x. Those are all in the I direction, so we can simply add them together. And then f1y plus f2y minus f3y, all in the j direction. And then f1x minus f2x plus f3x is simply the resultant x component, or I should say the x component of the resultant vector, frx. Okay? Now, if we want to know the direction and magnitude of that resultant vector, notice we have our frx and fry now. All we have to do is take the inverse tangent of fry over frx. We simply treat it as a right triangle because the x and y axes, which govern the direction of the unit vectors I and j, they are perpendicular to one another. So we're just dealing with right triangles here, which you know how to do. Or you should. If you need some help with that, let me know. The resultant vector then can be calculated by the Pythagorean's theorem. Just frx squared plus fry squared, take the square root, and there's the length of the vector. Now notice, be careful here. In the figure, you see fr is bold, you see fry is bold, you see frx is bold because the directions are important there. But then in the equations, you might be confused and say, well, where does the direction come in? We're not using the direction component of the vectors in the equations. We're simply using the scalar components, fry, frx, in the equations in order to calculate the angle of the vector from the x-axis. And notice that's what you always get here because we've got y over x. You're going to get the angle versus the x-axis. And the resultant length or magnitude of that force vector based on the sum of the resultants along the x direction and the y in Pythagorean's theorem. But again, the equations are only dealing with scalars. So notice we've got two kinds of equations now we have to deal with. We've got scalar equations, which you've been dealing with for a long time now, and we've got vector equations. And vector equations are a different thing, okay? But these two happen to be scalar equations, so you shouldn't worry too much about them.